PyTorch is, at its heart, a library for the Python programming language. Its primary purpose is to provide tools for building and training neural networks. We use it to create complex models that can understand images, process natural language, interpret sounds. Its origins trace back to Facebook's AI research lab, now Meta AI, developed as an open-source project. The library quickly gained popularity in the research community because it was designed to be intuitive and flexible. It enables a programming style that feels natural to Python users, lowering the barrier to entry for aspiring ML engineers and researchers. The reason many choose PyTorch comes down to key principles. First, an eager execution model. Every line of code runs immediately. That lets you run and inspect code step by step, making debugging far easier than define then run frameworks. This rapid, iterative workflow changed research and development. To understand PyTorch, you must first understand the tensor. Tensors are the fundamental data structure in PyTorch, analogous to numbers in mathematics. At a basic level, a tensor is a multidimensional array, similar to NumPy arrays, but they have a crucial superpower. You can move them to a GPU to accelerate computation. You can create a tensor from a simple Python list. You can perform standard mathematical operations on them, such as addition, multiplication, matrix multiplication. They carry data through your neural network from input to output. Let's look at a simple code example. Import torch. Create a two-dimensional tensor from a nested list. X bar torch.tensor 1.0, 2.0, 3.0, 4.0. Now perform operations on this tensor. Y srex plus 1. Every element increments by 1. The real power appears when leveraging a GPU. X-ray GPU, large X2, CUDA. Transfer tensor to GPU memory for faster calculations. Once we have our data in tensors, we need a way to train a model. This is where PyTorch's AutoGrad engine comes into play. AutoGrad automatically calculates gradients. Gradients are the cornerstone of model training and deep learning. Gradients tell us how to adjust our model's parameters, weights, biases, to reduce error. To use AutoGrad, tell PyTorch which tensors require gradient tracking by setting requires grad true. For example, x produce frar torch.tensor 2.0 requires basnatsu grad and suds true. PyTorch builds a computational graph in the background, recording every operation on tracked tensors. After calculations and a loss, trigger gradients with loss.backward. Loss.backward traverses the graph backward and computes gradients for tensors with requires grad true. Example, define y tra o xx and call y.backward. Then inspect x.grad. It yields 4.0. This automatic differentiation enables backpropagation, the workhorse of neural network training. Torch.autograd handles gradients. Torch.n provides model building blocks. N contains pre-built layers. N linear, nn.conv2d ReLU activation. Build models by defining a class that inherits from nn.module. Specify data flow in forward. A model architecture and a gradient engine are not enough. We need a way to measure the model's performance and a mechanism to improve it. This is where loss functions and optimizers enter the picture. A loss function, found within the NN module, quantifies how wrong our model's predictions are compared to the actual ground truth. Mean squared error, for regression tasks, cross-entropy loss, for classification tasks. Using one is straightforward. Instantiate, then call it. The scalar value computed by the loss function serves as the starting point for backpropagation, but it is the optimizer's job to use the resulting gradients to actually update the model's parameters. PyTorch's Optim module contains implementations of many popular optimization algorithms, such as stochastic gradient descent, SGD, Atom. To use an optimizer, create an instance with model.parameters, and a learning rate. The learning rate is a critical hyperparameter that controls the size of the steps the optimizer takes to update the weights. The training loop ties these concepts together. Clear old gradients, forward pass to get a prediction, calculate the loss, backward pass, update weights. PyTorch's power extends far beyond its core components. A rich and vibrant ecosystem of libraries has been built on top of it, making it easier to tackle specific domains. For computer vision tasks, there is Torch Vision, MNIST ImageNet pre-trained models like ResNet, and common image transformation utilities. For audio processing, Torch Audio offers similar tools. For natural language processing, the Hugging Face Transformers library, providing thousands of pre-trained models BERT GPT, that can be used and fine-tuned with just a few lines of PyTorch code. Another critical feature for real-world applications is the ability to deploy models outside of the Python research environment. PyTorch addresses this with Torch Script. Torch Script is a way to create a serializable and optimizable version of your PyTorch model that can run in high-performance environments like C++ servers or on mobile devices. You can convert your model into a TorchScript object using tracing or scripting, for example. Scripted model, torch.jit.script, my model. This scripted model can then be saved to a file,